Good morning, one and all. Welcome to another session on computer organization. This is Dr. Diana here from St. Peter's Engineering College, and we have been looking into the design of hardwired control system. A hardwired control system is what we are trying to develop, and we have seen a primitive design of the hardwired unit where we take an external clock signal, we use a sequence generator and a decoder from the clock to generate timing signals T0 to T15. And then we use the instruction register and divide it into parts, and the opcode part of the instruction register is given to another decoding circuit that generates signals D0 to D7. Based on these values, I am going to generate some control outputs. I need to tell which of the devices are active at what point of time and which device or which component or register will transmit data or will receive another data. All of these depend on the control outputs that I generate out of this circuit. Now we have seen three different types of instructions: memory reference instruction, register reference instruction, and IO instruction. We saw that the 4 bits of the MSB of the instruction register will indicate the difference between a memory reference instruction, register reference instruction, and IO instruction. So if you can see the 3 bits, bit 14 to 12 of the instruction register, if its value is 111, then it is either a register reference instruction or an IO instruction. Based on this value, we have started our flow chart for executing different types of instructions. We started and we understood that at till time cycle T2, irrespective of the type of instruction, the instruction fetch operation and the decode operation remains the same for all instructions, either memory reference or register reference or IO instruction. So time cycle T0, T1 and T2 are the same, followed by identification of instruction and then execution of instruction. This is the information which indicates at what point of time and with what control inputs the different types of instructions are executed. The first indicates an indirect memory reference instruction. The second one denotes a direct memory reference instruction, and D7I-T3 indicates register reference instruction. D7I-T3 indicates an IO instruction. We have seen 12 different register reference instructions which happen at D7I-T3, and we have seen 7 different memory reference instructions which are operated based on the values of D0 to D6 at time cycle, from time cycle T3 to time cycle T6. We have seen that some of the instructions consume up to time cycle T6. And then we started looking into IO connection. We have now connected IO devices through transmitter and receiver interfaces to the computer system. Now we are going to use this setup to understand certain instructions. Now all of the IO instructions happen when the value of D7 is 1, the value of I is 1, and at time cycle T3. So all of them are having the same control information D7I-T3. Now at D7I-T3, I am going to call it as P, some common value P. So all of the IO instructions occur with the control information P. And for an IO instruction, the format of the IO instruction has the first bit set to 1, followed by 3 bits set to 1, and then this is bit 12 to 15 set to 1, and bits 0 to 11 have the opcode. So I am going to have, or I am going to indicate my instruction based on bits 0 to 11 of the instruction register. So the instruction register 0 to 11 are used for opcode, but there are not many IO instructions available. So I will use only bits 6 to 11 of the instruction register. So this is the set of bits I am going to use. Now depending on which bit is 1 and which bit is 0, I am going to call that bit as BI. So my instructions are going to start from B11 to B6. Okay, depending on whichever bit is high in the instruction register. So I am going to have 6 different instructions under the IO instructions. Now I am going to see what happens when the value is P and B11. When the value is P, it indicates D7IT3 followed by bit B11 being set to high. This indicates an instruction called INP. The instruction is INP, which means input something. So I have to read something inside the accumulator. So the accumulator should receive data from which register? The input register. Now I am going to assume that the interface has already started working, and when I am executing this at time cycle T3, my data is available at the input register. So I am going to send data from my input register to the accumulator at time cycle T3. So my data is now received at the accumulator. Once the data is received by the accumulator, it means no more data is available in the input register. So I should indicate it using the flag. What should the accumulator now do? It should reset the flag bit FGI to 0. Clear? The FGI is also set to reset to 0 now. Once this is complete, we can clear off the sequence counter and go to the next instruction. The next instruction under this category has PB10. B10 indicates that the 10th bit in the instruction register is 1 and P indicates D7IT3. The instruction is OUT. OUT means I am going to send some data to the output device. So the data will be available in the accumulator. It should be sent to the output register, and when the output register usually is always ready to receive data. So the flag bit of the output register FGO is always 1. But once it receives some data, until it finishes sending this data to the output device, the output flag has to be set to 0. So I am going to reset my FGO to 0 till the output register completes its sending to the receiving device. Now there are situations when the output, once it completes receiving, the interface will know when the output has been completely received. Only after that, the interface by itself, it will set this flag bit FGO to 1. Until that time, this flag bit is going to be 0. The next instruction is called Next instruction happens when PB9. PB9 means bit 9 is set to 1 and P indicates D7IT3 and the instruction is SKI. SKI means skip if the input flag is 1. If the input flag is 1, then I have to skip my next instruction. This happens when I have to check my input flag first. So if FGI is equal to 1, then what should I do? I should skip one instruction. How do I skip my instruction? I should increment the program counter value by 1. Clear? Now this is happening with the control information PB9. Now the next control information we have is PB8. At PB8, we have the instruction SKO. SKO means skip if output flag is 1. So if my output flag is 1, which is FGO is 1, then I have to skip my next instruction by incrementing the value of PC by 1. So clear? So it gives, if FGO is 1, then PC value is incremented by 1. Then we have PB7. PB7 happens when bit 7 of the instruction register is set to 1. And P indicates that the instruction happens when T7 and T3 is the control flow. Now this is an instruction which is ION. It means interrupt enable on. We are going to see what is interrupt. We are going to see what is interrupt enable. For now, you just understand interrupt enable on is the instruction. It means I am going to enable the interrupt by using another flip-flop, which is IEN. The IEN is called as the interrupt enable flip-flop. Its value is going to be set to 1 if I execute IO on. And we have another instruction PB6 IOF, means interrupt enable off. Interrupt enable off means the interrupt enable flag IEN is, its value is reset to 0. So these are the input output instructions in my basic computer. So if I just look back into the set of instructions, you can make a note of these instructions. So we have bits, we have the control information given here and the list of all instructions, and we see how these instructions are executed. Now we will see what interrupt is and how an interrupt enable works. An interrupt is a signal given to the system to show that it has to process something else. Imagine I am doing a program execution. I am executing an instruction one after the other. And the computer now has some other important task other than executing my program. So it leaves my program then and there and it goes and looks into the other program. So when another program or another equipment needs the attention of the CPU, it can raise an interrupt to the CPU and ask the CPU to stop the execution of the current program and take up execution of another program. Such a signal sent to the computer or the CPU to stop the execution of the current program and do some other task is called as interrupt. So interrupt is a signal which is sent to the CPU to interrupt its action or to interrupt its activity. So this interrupt signal is sent to the CPU and when the CPU receives an interrupt signal, it stops whatever program it is doing and then it goes and attends to another program. Now, there are certain situations where the computer is really the CPU is busy attending to some other task. So, it doesn't want another program to interrupt its activity. Under such condition, a flag can be used by the CPU, which is called as the interrupt enable flag. The interrupt enable flag is set to 1 by the CPU when it is doing a normal task. But when it is using or doing some special tasks, it just disables the interrupt enable flag and sets the IEN flag to 0. When the IEN flag is 0, it means that it is doing some important task and it should not be interrupted. So, when the interrupt enable flag is 0, it means that the other interrupts cannot be enabled or an interrupt signal cannot be sent to the CPU. Clear? So, an interrupt flag or an interrupt enable flag is used by the other devices to communicate with CPU, and the CPU waits until the interrupt is raised. So, when an interrupt is there, it services that interrupt. It does whatever the interrupting device asks for, and then it continues with its normal program execution. So, when the CPU wants to do something important, it is going to reset the enable flag and shut its door, making sure that none of the interrupts are raised during that period, and it completes its important task. Once it completes its important task, it again enables the interrupt enable flag to 1 so that other devices can make an interruption. Why do we need an interrupt flag? The reason why an interrupt flag is required is that, imagine the computer that we saw here. This is how an IO device tries to communicate. And when the IO device is trying to communicate with the CPU looks into the FGI flag and FGO flag before every instruction execution. So, at every instruction execution, what it does is, it goes and looks at the FGA flag, FGO flag, and then it starts with execution. And whenever the input is ready, only then the flag is set to 1. So, until that time, the CPU continuously goes and looks into the FGA flag. Right? So, imagine a scenario like this. I have a class. I am taking a class for few people. I have asked somebody to write down something. Once I have asked them to write down, I have given that data to that person, and every second, without taking a class, I keep on asking, is that ready? Have you completed writing? Like that, I keep on asking. This is a very similar scenario. CPU has a lot of tasks, but it is waiting for the input register to give it some input. So it keeps on looking at the input flag, FGI, without doing its important task. It is going to look into that FGI. So without me taking class, I am going to keep on looking at that person to check if they have completed writing. This is a very hectic task. I don't do it like that during my class. Right? What do? I give whatever has to be written to that girl. I tell, once you complete writing, you just tell me that you have completed. That is what I do, right? What she will do? She will interrupt my class. When I am still taking class, she will interrupt me and tell that it is complete. So the same way, the CPU also instead of going and checking on the input flag continuously after every time cycle, it will keep on doing its normal execution until the interrupt is raised by the interface. So the interface, once the data is ready, it places in the input register, it raises the flag FGI, and then instead of the CPU keep on looking at the FGI flag, when the FGI flag becomes 1, it sends a control signal to the CPU. That control signal is called as interrupt. When that interrupt raises, the accumulator then looks into the FGI flag and understands that some input is ready, then it receives that input. So it need not keep on looking into the FGA flag until the interrupt is raised. Are we clear? So an interrupt is a signal which is used to tell the CPU when certain things are ready. The same thing is going to be done with the output circuit also. In an output circuit, instead of the CPU waiting on the output flag to become 1. When will the output flag be 1? It is initially 1. So when I give some data to be sent to the output device, I put it in the output register, and then the output flag is set to 0. When the output flag is 0, the output register is trying to send that data into the output unit. The output unit is a very slow unit and it receives the data bit by bit. And until it completes receiving that data, the flag output or the FGO bit is 0. So if the CPU wants to send something to the output unit, it can only send 8 bits at a time. So it sends the first 8 bits, puts the FGO flag to 0, and it keeps on looking at the FGO flag until it is ready, and so that it can send the rest of the 8 bits. So the CPU is not able to continue with its regular execution until the FGO flag becomes 1. To avoid this only, we are using the interrupt system. So anytime the external devices become ready, they set the respective flags and then send a control signal to the CPU called as the interrupt. Once the CPU receives any of the control signal and interrupt signal, only then it goes and looks up into the respective flags. It looks up into both the input flag and the output flag and checks what operation it has to do and proceeds further. Until that time, it will not try to look upon these flags. So this is how an interrupt works. This is how an interrupt works, but the interrupt cannot be raised when the computer is doing something very, very crucial, which is why we use an interrupt flag. So when the computer is doing something very, very important, it disables the interrupt enable flag, putting its value to 0, so that interrupts cannot be raised at that time. So when the input device is trying to send something to the CPU, if the interrupt enable is not available, if the interrupts are not enabled by the CPU, the interface will have the data with it and it will keep that data with itself and be ready until the enable flag is switched on. When the enable flag is switched on, then it immediately sends an interrupt request to the CPU so that the CPU can now start reading data from it. So this is how an interrupt system works. We have seen that this is how the instruction starts executing. At time cycle T0 till T2 it is going to be the same, and then we have seen how different instructions are executed. Now we will see in the next session how an interrupt can be used to interrupt the normal flow of execution and how an IO instruction can exactly be implemented or executed without the CPU having to wait on the input and the output devices. So we will look into that in the next session. For now, you just understand that interrupt is a signal sent to the CPU so that it can pause whatever it is doing and then attend to it. Every time the CPU receives an interrupt and goes to that particular device for doing what the device is asking, it is called as servicing of the interrupt. So, external device can raise an interrupt when the interrupt enable is on. If the interrupt enable is off, the other device has to wait until it is enabled. Once the interrupt enable is on, then it can send an interrupt signal to the CPU. The CPU will receive the interrupt signal and it will service that interrupt, do whatever the external device is asking it to do, and then it will proceed with its normal execution. So, we have seen an instruction execution here earlier. We will see how interrupts can change this normal flow of execution in the next session. For now, I conclude here. I request all of you to stay home and stay safe until we physically meet here in the campus. Looking forward to seeing you all soon in the campus. Thank you, one and all. Stay home, stay safe. Thank you.